Again, welcome everybody. We've got a very niche topic today. The idea of electrifying HVAC subsystems with RETScreen Expert. Now, it's kind of maybe an obscure title, but the idea here is that it's one thing to take an entire building and essentially take all the heating and cooling and electrify that. If you've got a fairly complex facility, and it's funny, Jason out there from Toyota, I'm always reminded your building because you got like a large manufacturing space in the front. You have an office and you have a rooftop unit on an office. And I'm going to kind of model that situation where you don't have the sub meter on the office. You really don't know how much energy and load is in that small subsystem, which is serving the office, but you want to be able to electrify it. So we're going to use the tools available in RETScreen to do that and maybe show you a few other things. So just getting started, we'll start off with a quick overview of some of the learning resources. And then I'm going to talk about the difference between energy and fuel. Now, many of you, if you've used RETScreen before, will have seen these terms, but I want to make sure all of us are really clearly understanding what the terms energy, fuel, and I've introduced another one called net energy means within the RETScreen model, because it's going to be important today that we know which of these things that we need to use. And we're going to actually be working with two models in RETScreen. There's essentially the whole facility feasibility model, which most of you are probably familiar with, ventilation envelope, and all the different elements that you would normally see in a whole building model. But we're also going to dive in and take a look at the power heating cooling model. So for some of you, this may be new. I know some of you have seen it before. I'll show you in a few minutes where it is. And we're going to use these two models interchangeably. You can't see them. You can't see them at the same time on the screen, but you can switch between contexts and you can take data from one and plug it in the other one. And that's going to be what we're going to do here. We're going to use the traditional energy model in RETScreen to model the entire building. In fact, I'll use an archetype to do that. And then I'm going to separate out the pieces that I want to electrify. So let's say the office out of a much larger facility. I'm going to take the data that RETScreen generates for that office. I'm going to pull it over into the power heating cooling model and then electrify that particular part of the HVAC load. So that's kind of the objective today. And then I'm going to show you how to optimize the sizing of that using the power heating cooling model. Adam will take us through a couple examples, the whole facility doing this, or where you have no historical data using RETScreen to model a building. Maybe you're part of a campus and you have multiple buildings, but you don't have a meter on a building. So you want to electrify that building. So how do you do it? Well, you model the entire building, generate the bill as it would be, and then use that in the other tool, the power heating cooling model, otherwise known as PHC model today. So I'm going to do most of it in slides, just so that there's a record of the methodology, but I will provide the files that we're going to use at the end. There's going to be two of them. And then eventually what we'll do is we'll tweak that file because to begin with, we'll find that, hey, we really don't have a return within the lifetime of this heat pump. But what can we do to size this differently, right, to make a hybrid system and ultimately then get a reasonable return within the life of the equipment? So, and then I've got a couple of notes about modeling HVAC systems in detail, just to reference to some other videos that we've created in the past, because that would be relevant if you're going to do this in more complex systems. So, how do you find this thing called the power heating cooling model in RETScreen? Now, again, some of you have probably done this before. I'm sure there's probably some people that haven't. So I'm going to pop in here. And so here I have my RETScreen file. And across the top, I go to energy. And this is basically this is the energy, the 34 to 40% reduction in energy archetype from RETScreen from the virtual energy analyzer. That'll be my starting point. And basically, this is what you normally see in the energy model in RETScreen if you click on the energy tab. But I'm going to show you a little trick, which is pretty neat. We go over to facility and we click on the facility type right at the top, and we scroll right up to power heating cooling, right? So it essentially doesn't change anything. You look at it, everything else seems to be the same until you click into this energy model. And now you get a completely different model, right? Now, do the numbers go back and forth between these two? No. When I change context, does it delete the data in the other context? No. So we can use these things with basically in parallel, okay? And we can move data back and forth. Typically, we move data into the power heating cooling model in order to do the extended calculations that we want to do. So that's what we're going to work with today, is how to use this power heating cooling model in conjunction with the traditional energy model, or what's otherwise known as the real property model in RETScreen. So I'm going to jump back now to my slides and just go through a few basics here. And again, if there's questions, um, even things that you think may not seem to be relevant, but it pops into your head as we're going through this, please don't hesitate to jump in the chat there and let us know about that. Adam or I will be monitoring depending on who's presenting. Okay, the one thing I always like to point out with RETScreen is there's lots of support for this. So, for example, the templates and case studies. So from the main screen in RETScreen, there's a thing called case studies and templates down here. Have a look at those. There's about 100 and something various different types of circumstances or situations that are being modeled in RETScreen. A template is a hypothetical situation. A case study is a real situation. And for all of these, there's textual descriptions and inputs. You can use these for self-learning, but there's also then the solved problem, as it were, in RETScreen if you double click into it. So there's some great examples there. In addition to that, there's a lot of help. Most of you have probably seen RETScreen's YouTube channel, which is great. Lots of videos, long and short up there. But the other thing about that YouTube channel is it's linked directly in the software by this e-learning button. So you can click on that e-learning button. For example, this is a pump analyzer here within the energy model, and you want to learn about pumps and how to use this particular model, then what you click on that and it'll take you right to that video. I think this one may be 3 or 4 minutes. So rather than going through a longer video, it kind of takes you right into the details that you want. And then in addition to that, many of you have seen it, is the textual help. When you hover over any of these labels, typically you'll get a text box and maybe a couple of drill downs in there, which are quite useful as well. So make sure you keep tabs on that. Now, when it comes to the power heating cooling model, in addition to any of this, there's also quite a bit of documentation. Adam and I will show you where that is throughout the session in the e-textbook that's available for RETScreen under the help section. So for those that really want to know how this power heating cooling model works, and what it does in short is it actually determines the loads, whereas RETScreen typically deals with kilowatt hours or energy in the energy model. But when you go to the power heating cooling, you're actually dealing with the actual loads, the heating loads. And that gives you the ability to sort of begin to preliminarily size things like heat pumps or electric heat or electric boilers. We're going to talk about heat pumps today, but it could be used for any of those things. So in addition to any of the help functions or case studies, there's always the virtual energy analyzer. It's the core of the net zero planning tool. If you haven't looked at it, have a look at that one. Different subject, different video, but the net zero planning tool. But these archetypes, right, which are sort of prototypical situations, prototypical buildings or archetypical buildings in RETScreen, which can be used to essentially do a virtual energy audit in a sense. If you've got a building type, you identify it, you scale it to your building, and then you see what can be had in terms of net zero or decarbonization strategies. That's a great way to use it. What I'm going to use this for today, the virtual energy analyzer, I'm going to pull up a building. I'm going to use it as a starting point just for the demonstrations I'm going to do. So it's pretty useful for a number of different purposes. So have a look at that. And the virtual energy analyzer doesn't just give you facility archetypes, but it also gives you measure or action archetypes as well. In this case, heat recovery in a residential application. All right, there's a number of detailed archetypes. Some of them are energy reduction archetypes. We'll be using those today, but there's also deep carbon archetypes. Well, striving for 80 to 90% carbon reduction. Now, we'll achieve in our subsystem close to 100% carbon reduction by electrifying that subsystem. So it's kind of a different piece. So we're going to use these as a starting point, but we're going to use the power heating model to go a lot more deep. Now, so I'm going to introduce some terms. I'm going to introduce the term, well, energy and fuel. And if you've used RETScreen before, you'll see that. But if you haven't seen it before, we'll cover that off very quickly here. But then I'm going to introduce the term net energy. And what I'm talking about here is how RETScreen allows us to take into account the internal heat gains, lighting, computers, solar gains, all those kinds of things that contribute to displacing heating fuel in a building or increasing cooling load in a building. So we're going to sort of dissect this one a little bit. And a lot of people will refer to RETScreen at times as a simulation tool. And I think that's probably not the best term. RETScreen is a model, and it's an energy accounting model. It accounts for all the energy that comes into a building and leaves the building. So, and I think the way to think about it is it accounts for all these things, okay? It's a simulation model which typically operates hourly. RETScreen doesn't operate hourly, typically monthly or annually. The simulation models have a lot of interactions that RETScreen doesn't model. Now you might think, well, that makes RETScreen deficient. Well, in fact, no. RETScreen was designed to be sort of an expeditious tool to getting to an answer relatively quickly. It has a fair bit of detail at times, and most simulation programs have way more detail. So the idea is, how can we get to an answer with a reasonable amount of data in a reasonable amount of time? And today's a good example because, we could do a lot of detailed calculations on sizing heat pumps or trying to figure out how much energy is going to a different part of the building. But RETScreen gives us the ability to do that relatively quickly with a minimum amount of inputs or data. So the model underlying, there's a pretty simple picture, right? But the model underlying all this in RETScreen is represented by this picture here. For those that have taken some of the more detailed RETScreen courses, you have seen this before. But basically what this does is allows us to see where fuel, what is fuel? Fuel in RETScreen's definition, and maybe I should have defined this in words on the slide, but fuel is anything that enters the system that you purchase. So electricity and natural gas today are going to be the fuels we're dealing with. The heating and cooling systems take the fuel and basically convert it to energy, right? So natural gas fuel is converted to heating energy, which contributes to heat in the conditioned space. The chiller will take electricity as a fuel and convert it to cooling energy or cooling utility, which then cools our conditioned space. Now, we can set aside the process loads and those kinds of things. We're not dealing with those today, but they do interact here. The key thing I want you to see here is that within RETScreen, in addition to this boundary on the outside, which is the boundary across which we purchase fuel, or we lose heat, or we gain heat, or we reject heat from the boiler or from the boiler and the chiller. In addition to that boundary, right, there's also a conditioned space boundary internal to RETScreen where it deals with the interactions between, right, the heat loss and the heat gain, which could be through ventilation, well, primarily through ventilation in the building envelope, okay? The heat gain from lighting and other loads in the space, which contributes to heat and displaces some of the heating energy required, ultimately displaces the fuel required, but also contributes to the cooling requirement and increases the amount of fuel required for cooling. So it's this conditioned space boundary that allows RETScreen to deal with the interactions between internal heat gains in the space and the actual heating and cooling of that space and eventually the fuel required for that. So within the include screen, which is typically the screen you'll see when we do an energy model in RETScreen, there are a number of different regions. So anything sort of above this line, it's kind of not really noticeable. There's a line here which divides the systems that convert the fuel to the energy. And down here we have the systems that utilize or require energy. Okay, so below this is energy, above this is fuel. Now, but we can display the fuel required by each of these systems or the fuel saved depending on how we set the switch at the top of the screen. So heating and cooling systems, right? Could be a rooftop unit, could be a hot water heater, could be another part of a rooftop unit. Those are the things that provide the heating and cooling energy to the systems that require it down below. And then we have the systems that use energy, right? Where there's no conversion of fuel to energy. So for example, lights, fuel and energy is one and the same thing. Same thing with fans and pumps, right? So the electricity that comes in is used directly by those things. Now, what you'll notice here is RETScreen actually gives you 3 columns to look at. And in today's session, these 3 columns are going to be really useful. There's the heating, right, energy, right, or heating fuel. In this case, we're displaying fuel saved. There's the cooling fuel, because it says fuel over here. And then there's electricity, which is for, powering the lights and other kinds of equipment, also called the fuel. Now, so again, energy is what's required, right? So in RETScreen, when you look at the screen, you'll see that at the top of the screen, actually we'll get to it eventually, it'll say energy model, and that's where you get to this screen here. So ultimately, those things that require energy, right? Heating, cooling, and electricity, right? So your building space needs heating energy, it needs cooling energy, but there needs to be fuel to supply that, okay? And that's the difference between these two things. So ultimately, right, the difference between fuel and energy, as it's displayed in RETScreen, is also impacted by these things called the internal heat gains, right? And we can control how much of the lighting energy, right, and essentially fuel as well for lights, impacts upon heating and cooling within the space. So here we're looking at this screen, energy in the proposed case. Doesn't matter whether it's proposed or in this situation, proposed or base case, but basically the energy here, right, is the energy required by the building envelope or the ventilation in the office, right, less, and this is where I'm going to introduce the term net energy, less the internal heat gains contributed by the lights in this situation. Okay, so the net energy is what you're actually appearing here. So this actually could be called net energy. When you dig deeper into the systems, right, you'll actually, I'll show you this, right, where the net energy, where the fuel is, and where the energy is. So let's start off with an example where we're doing ventilation. Okay, so up here we have ventilation. And by entering in the flow of air, entering in the schedule, and whether we're heating or cooling it, in this case, we're going to be cooling it, right? Then this number here that RETScreen calculates, required of the boiler, is the heating energy. Okay, that's required of the boiler. Now, RETScreen, what it does then is it takes all the lights in the building, right? The sum of all the lights and electrical loads, right? And it apportions it, right, according to the loads or the amount of energy required by each space. And basically, it reduces this 228,000, right, by by a certain number. I'm not going to calculate it here, but basically it's 131,000 by 75% by the time of the year by a little internal safety factor for RETScreen. And it comes up with a number, which is the difference between the 228,3 and the 176,000. So when you look at your include screen under ventilation, you don't see the 228 as the energy, you see the net energy required, right, which is the 176. That net energy, right, so this is displaying energy, but in fact, I'm calling it net energy. That 176 then gets divided by the efficiency of the heating plant, which would be specified up here, to determine the fuel required in kilowatt hour terms. These are all in kilowatt hours. So here we have the energy, here we have the internal heat gains, right, which then reduce the heating energy to the net heating energy for ventilation. And then we have the fuel required to meet the net energy requirements, right, at the efficiency of the heating plant. And the same thing happens on the cooling side of things, right? So RETScreen calculates the cooling energy required to cool this airflow for the cooling season. It adds to it. So before, remember, we subtracted, right, because the lights contribute to heat. But in this case, the lights contribute to cooling load. So we have to add, right, the impact of the lights, again, apportioned appropriately for the cooling season, whatever factor we put in. So we have the cooling energy of 45,000. We have the net cooling energy of 73,000. But then we get to reduce, right, because we divide by the coefficient of performance of the heating or the cooling system. And here we see then 18,000 is the fuel required to meet the net energy requirements, which takes into account both the internal heat gains, the lights, plus the actual physical requirement to cool the space against, in this case, ventilation. So it's important to really understand those things. I know that's a lot of detail here, but when it comes to actually using the output of RETScreen and using it in the power heating cooling model, we need to, in fact, we end up using the net energy requirement. If anybody has worked with building codes and sometimes you're required when you're designing a building to specify the TEDI, the thermal energy demand intensity of the building. And in fact, RETScreen can calculate that because TEDI is defined as the envelope requirements plus the ventilation requirements minus the internal heat gains divided by the floor area. Well, RETScreen has all those numbers. I was doing a workshop a little while ago with a company that does that kind of simulation and modeling work. They said, well, couldn't RETScreen do that? And in fact, I sent an email after RETScreen and the next version that was there because all the numbers were there, just a matter of displaying the result on the screen. So RETScreen does have, it seems like some of this stuff is superfluous, but it's quite useful when it comes to actually modeling these systems. Keeping on my time here, I think we're good. So now the whole idea here today is about being able to take a subsystem of a building and model it, and using the energy model on the essentially the real, what's called real property side of RETScreen to generate the inputs for the power heating cooling model. So why would you want to do this, right? So, for example, the heating cooling loads are not known for part of a building or its subsystems. Jason, there you go. I was going to put your plan up there, but this is more of a warehouse. So you might have a warehouse with a large area, and this one's pretty cool because it's got lots of solar panels on the roof. You got a small office in the front. You want to put an HVAC or rooftop. You want to replace that rooftop unit, but you want to know how to size it and build a business case for it. Well, that's what we're going to do here today, is exactly that. So you don't know what the heating and cooling loads are to begin with, but we can use RETScreen to estimate what those are and then use those to do the project feasibility. In some cases, the fuel consumption isn't known for the whole facility or part of it, right? Which is the same thing. So maybe it's part of a university or a college campus or a multi-building campus, right? The impact of the internal heat gains in equipment is not typically known. That's not something that's very obvious. So RETScreen has that facility to calculate. And today, as I said, we'll use a warehouse with an office attached as our worked example. So it's really a way to use RETScreen to provide information where you wouldn't otherwise have it. Now, you could argue, you could stick a meter on that rooftop unit and meter it for a year and get the heating and cooling fuel required. Yes, you could, but that's going to be pretty expensive. This is actually a much more expeditious and inexpensive approach. So Adam, you're going to kind of walk us through these two methods here, are actually method one, which is the whole facility where you know the historical data, you know the floor area, and it's going to help you to estimate what the heating and cooling loads are. You'll enter your efficiencies and come up with an answer. And then you'll take us through an example where you have no historical data, right? And then eventually what I'm going to do, so we're actually going to pass through this methodology 3 times today, okay? Adam's going to do it for the example 1 and example 2A, right? And I'm going to do it for the partial facility. I'm going to dig down. I'm going to use an archetype. I'm going to do a lot more detail. So Adam kind of will do it at a high level, and then I'll dig down. And when we're finished, we'll jump into RETScreen and we'll tweak our model to make it more maybe financially and carbon attractive. Adam, over to you.
Yeah, thank you. Yeah, and I guess kind of the key to this is step 1 here, this 2-path whole facility with electricity and natural gas data. That's kind of the core of what we want to learn today. The other 2 methods are kind of how we can use the other parts of RETScreen, which maybe you're a little bit more familiar with, to pull data from, to kind of generate some of the data to bring it into this power heating cooling model, or cooling and heating model in this case. So for step 1, kind of the basic site data you need, which hopefully a lot of this data you can get for your site, or the couple pieces of information you can kind of come up with within RETScreen as well. So we need historical data. That's usually relatively simple to get. We need floor area, which again you could probably get. It's heated or conditioned floor area, not just your real estate floor area minus basements and things like that. So it's all conditioned spaces. We need our heating and cooling load in watts per meter squared. And then we also need our heating and cooling efficiency, or seasonal efficiencies of our heating and cooling plant. So 3 of those 4 pieces of information you can probably go out and get relatively easy. It's that heating and cooling load, the watts per meter squared, which we're going to have to kind of use a few other pieces of information we have there to kind of come up with. We kind of tweak some numbers, reconcile back to real historical data to come up with that watts, heating and cooling watts per meter squared. So we're going to go through a few step process, as I said. The first one here, it's kind of somewhat a 3-step process. You define your heating and cooling systems in your base case, and you come up with your peak heating and cooling loads, and then you go on to your proposed case and implement kind of your new systems, or even kind of improving your current systems there as well. Now, once I'm done that, I'm going to kind of rewind a bit. We're going to go back to the feasibility models, pull out this information from a model, bring it over back, kind of the same process to kind of reiterate it back into that power heating cooling models.
And you'll be pulling out the data for the whole building, whereas I'm going to go in the 3rd time. I'm going to pull out the data just for the subsystems that we want to electrify. So that's kind of the focus of today eventually.
Yeah, so here's kind of a little more detailed screen on what we're going to, on the combined heating and power screen. So and we're going to concentrate mostly on the heating side in terms of the slide. That is, cooling is already electrified. The goal of electrification is usually on the heating side. The process is exactly the same. You need your seasonal efficiencies, your watts per square meter, but we're going to kind of show mostly on the heating side here. So And then we're going to get to the financial case and the carbon case as well. So there is lots of help out there on this one. So this is actually very well documented in RETScreen. I might show a simple graph later to kind of how we deal with the peak load there, but there is a very well laid out case study and example in the help there on how this model was derived here. So I'd say suggest read through it. It is very informative, kind of helped me a lot understand what's going on behind the scenes here. So the whole facility, we can, with kind of on each side, heating and cooling, 5 or 6 pieces of information, we can get this. The goal at the bottom here is this net peak heating load and net heating energy here. So this we want to come up with this 98.5 kilowatts and 216,000 kilowatt hours here. So how do we get there? We need to put in our heated floor area. So that's why I said it's your heated conditioned space. It's not just, well, if you look at a real estate listing and you get 3,000 square foot, but there's a 1,500 square foot basement. If that basement is heated and cooled, it needs to be included in there. Then our fuel type, we have natural gas, and setting all that up, the fuels, things like that, that's the same in this section of RETScreen. You can have biofuels, you can have all sorts of other different fuels in there, oil, propane. Then we need our seasonal efficiency. So in this case, we have a 70% seasonal efficient boiler furnace. I'm not sure at this point. Doesn't matter as long as we have the fuel and the efficiency. Then in red there, we have our heating load for the building. So if you're not sure where to start, there is a kind of a quick way to get a number in there to kind of start tweaking it. If you go into the help in RETScreen, so if I hover over this title of the heating load and you click into there's a building heating load chart here. So if you take your heating design temperature, which you can also find in RETScreen as well, so you go back to the facility page or location page, you can find your heating design temperature, make a quick estimate of kind of whether your building is poor, medium, good insulation, and kind of go in there and get a quick number to start where you want your watts per square meter. But again, we want to bring that back to real data at some point. We don't want to be just tweaking data. So put a number in there to start. That is going to give you your total fuel consumption here. This is this 51,781 meters cubed. That's what we want to reconcile back to your bills. So if you jump in here, you put in this 39 watts per meter squared. If that 51,000 approximately is what you use, perfect, you're done. If not, a little bit more needs to be done. So first, you need to look at your domestic hot water load in your building as well. So if you use electricity, put 0 here. If you use natural gas, you do need to make an estimate of what percentage of your natural gas is hot water. There's a couple different ways you can get that information. You can look at your annual bills for your natural gas and kind of subtract out the base load throughout the year, which you can see kind of exclusively in the summer, as long as you don't have any other processes using gas in your building. Or you can use, again, the second method here where we can pull that out from the RETScreen models as well. So put that in there. That then further kind of reduces that fuel consumption to reconcile back with. Then I'm able to kind of tweak up this number, heating and cooling load for the building to get that 51,780. So once I've done that, that's kind of the building as is. But let's say I wanted to do some energy efficiency measures in your building. So you could also do that. We always recommend reduce your waste, maximize efficiency, then optimize supply. So doing those first 2 steps before you actually go out there and buy a new heat pump or a new heating and cooling system. So that can reduce our net peak heating load and net energy a little bit before we do that. We don't need to buy as big of a heat pump to meet the heating and cooling loads in our building. In this case, they've done end use energy efficiency measures that are approximately 44% reduction. So this was taken from a RETScreen archetype. So it's fairly deep retrofit there, but you can take these numbers or find them from a feasibility model, or if you've had any kind of audits done on your building, estimates of savings that could be done for things like insulation, air sealing, that kind of stuff. So the goal at the end of the day is we want to get this number, these 2 numbers here for heating and cooling. So we want that 98.5 kilowatts for heating and 90.6 kilowatts peak capacity for your heating and cooling systems in your building. That's kind of the general sizing you would need if you were to go to meet 100% of your energy needs in your building. So next step, go over. That's what we have here. So we see we have 98.5, 90.6. Always go out to the contractors before you buy all those things. You can't always go out and say, I need this exact kilowatt system. You have to kind of buy what is available to you in most cases. So kind of use that. You can use the tool a little bit further down the line to kind of size
And,
that up. If you want to go
and
smaller or bigger, bring in the hybrid system options as well. So go
And
ahead.
just to be clear, like we can use different units of for load there, peak system load. We're using kilowatts. That's like the thermal kilowatts. So 98.5 divided by 3.4, right, would be, or sorry, multiplied by 3.4 will give you the BTU per hour divided by 12 is going to give you the tons. So you could specify this as tons as well. But to be consistent with all these, we're just going to leave the units of load at kilowatts. But that's not electrical load at this point. This is actually the thermal load, whether it's for heating or cooling.
So yeah, the next step, that's actually where we actually start to define those systems and their electrical capacity. So in this case here, in the blue above here, we've done our cooling system. So we can come in here, it's a compressor. So we've just kind of matched it to meet 100% of the load. Again, always go out and check with the contractor what systems are available to you. So we've matched, so we have a 90.6 on the capacity, which gives us 100% of our load. And in this case, with cooling, you kind of have to meet 100% of your load. There's no kind of backup peak load cooling systems that aren't, because it's all electricity. So you do kind of have to get a system to meet 100% of your needs. So the cooling delivered is 100%, and the demand and the capacity is also 100% here. On the heating side, that's where we can go out and get a little bit more creative and necessary. In this case, it has been matched to meet 100% of the load, or it's probably actually 99.9% of the load. Because if you see, after we jump over onto this next screen, so we're over here right now with that 98.6. If we go to our proposed case system, so and then you can actually, sorry, on the heating system here, you can pick a number of different technologies. You can do single fuel, multiple fuel. So if you do things like biomass boilers, things like that, you can kind of split up how you do that as well. Kept it relatively simple to start out with here, but there is a lot of flexibility with all of the different types of systems you can model here. So now we get over into our proposed case system characteristics. So on the heating side here, you'll notice it says it's 100%, but we have a little bit of a flag here. It says we need a peak load heating system. So in this case, just to kind of show, I think it's actually 100%. So we would be covering the heating with electrical load here. But just in case, and Stephen will explore this later, kind of how we can take advantage of this a little bit more. In this case, it's only using 0.01% of our heating is peak load heating system. So I wouldn't keep my natural gas boiler personally if it was only doing 0.01% of my heating. But you can kind of click that peak load heating system, use your existing system, or sometimes even buying a new natural gas system, depending on the situation, costing, carbon, things like that, to kind of make up that remaining load. And kind of where that gets creative, or how that's kind of thought through, is in that help section. There is a graph here that I find quite handy. This is kind of the number of hours at the percentage of peak load heating. And it's this kind of peak here where we can take advantage of some things and kind of somewhat maybe chop that off and not have to meet 100% of our load electrically, depending on what your goals of your organization are. Because there is kind of ways we can get a very significant portion of our carbon reduction, if that is a goal, with kind of still chopping that off and using a natural gas or a fossil fuel as your backup kind of peak load heating system. Because the number of hours that is running is actually very small. So we don't need to kind of oversize our system electrically for only a very small percentage of the time. And you
it's interesting, Adam.
probably
It's
already have a lot of built-in capacity with that natural gas boiler. So,
it's interesting,
but
Adam, on that graph. The big curve there. Goes upwards at about 60 to 70%, right, of load.
yeah,
So when I build this hybrid system later on, I'm going to use a number like 70%. I'm going to drop it down, or maybe 65%. So what I'm really going to end up doing is just chopping that off and sizing the system much lower to still meet 98% of my energy.
yeah.
But I'm not meeting, anywhere near the 100% of the full demand. It's those few hours a year we're going to let the gas do the job and take a little bit of hit on carbon. So yeah, good point.
Yeah, this is a very real thing. I actually did this in my house. I was able to almost cut my heat pump size in half, and I only run my natural gas backup as I think it's like 5 or 6% of the time I calculated there. So, and again, if you've bought a new furnace or boiler in the last 5, 10 years, you maybe don't want to pull out a brand new boiler just to put a heat pump in. So you can kind of do this hybrid system and take advantage of both while still meeting your goals of your organization. So. Then we can see we get into the carbon reduction. So in this case, in Ontario, we've taken all of the load. Oh, actually, no, this example here is a bit different. So we actually see this graph here. The base case, they've actually only have the electric is only it's under 50% of the capacity, while the remaining is the peak heat load system, which is probably the fossil fuel, but they still reached an 87.4% reduction. So you can actually significantly size down these systems and still use kind of the hybrid system and get a major carbon reduction there. So again, we'll bring in some of the financial case. Now, depending on prices, natural gas, electricity, cost of carbon, these things that can change these things drastically. So, but right now, this situation with a 2% inflation rate and a project life of 20 years here, your simple payback is at about 15, 16 years. So it is within the life of the project. So you will be starting to see positive cash flow at the end. And again, but also if your systems are failing or nearing end of life, that could drastically change this kind of financial
And
case. So
and
it's, it's in,
in
yeah,
that
go ahead.
case, you're not going to carry the full cost of the heat pump.
Yeah.
You're going to be carrying the marginal cost of the heat pump over, for example, the traditional like for like replacement. And this also doesn't account for any carbon incentive, which may
Yeah.
come in the future, or any other incentive. So there's lots of ways to improve the business case, but that's the sort of the straight up first blush of what it looks like.
Yeah, yeah. Our goal is to improve the business case, but you also upfront right now with how things are changing, you do have to be honest with the business case and kind of outline what your goals are and align with those. So now moving on to method 2A. So you have no historical data, or you have a RETScreen model that's already been built, or so you want to pull out a portion of that, which Stephen is going to do. We can actually use both sections of RETScreen to come up with what we've just done. So we can go in here. So in our using our energy model, so heating, cooling, electricity interactions, we can go into our include measure screen. So we've already got this building has all been built up. Either you've done it or someone else has done it for you. Or even if you want to come in here and just get a rough guide of decarbonizing or something like that in a specific jurisdiction, you can use these archetypical buildings to kind of pull data over and explore what would happen. So in here, we have our heating energy and we have our cooling energy. So the number we're looking for is actually just the total at the bottom. And on the heating side, we can also pull out our hot water here in this case. So we do have 24,000 equivalent kilowatt hours, depending how it's heat. I'm assuming it's natural gas in this case. So we would actually want to take that out as a percentage. So this actually makes it even easier to find that hot water percentage here. But we want our net heating load minus the hot water, and then our cooling load as well. So those are the two numbers that when I took them from the bills earlier and I wanted to reconcile back, these are those two numbers I'm going to reconcile back within that power heating cooling model there. So just if you have your model or you want to build your model, highly suggest doing that. It is just also good practice with RETScreen. Then we can take those numbers back over into RETScreen. So we use the 385,000 to calibrate back there. So we have our total peak cooling in kilowatt hours, 385. So we've adjusted that watts per meter squared to reach and match that number, or equivalent in natural gas is 51,781. So same thing on the cooling side. Now that brings us back over. This is a little bit different data than we looked at before. So we do see that it is 176 kilowatts. In this case is our peak heating load, and 113 kilowatts is our peak cooling load there. So a
The
little bit
reason
different
that's
number.
slightly different is you don't
Yeah.
have any end use energy efficiency
Yeah.
measures on the heating cooling
Yeah,
side.
we didn't remove or go in and do that. I think it was 20% on cooling and 45% on heating. So we do need the full system capacity here as if we didn't do any efficiency measures. So determine, yeah. So if we wanted to bring that back in there, sorry, I forgot this was in here. Determine the fuel and energy savings. We can also get that from back in the feasibility model. If you go onto the comparison screen here, there is also those numbers. So if this is where you've maybe worked in before. You've put this project verification. They should actually have their historical bills there. But if you go below that, there is savings calculations here. You can see the amount of fuel saved is also on the include measure screen in green here. So you could do the calculation there, or you can let RETScreen do it. And they've told you the fuel saved on the heating side from whichever measure. So it's air sealing, demand control, ventilation, and heat recovery in this case. They have a 43.9% reduction on the heating, and then that 19.5% reduction on the cooling. So then we bring that back in there. That comes back into the power heating cooling model at the bottom there, that 43.9, 19.5, which then reduces our heating and cooling energy requirements for the building there. So we've kind of insulated, air sealed, made our building tighter. Don't need to buy as big of a system, which is going to save us a lot of money up front. So then we follow the exact same process we've done before. So we go into our proposed case cooling systems, and we've matched them 100% here. So they're doing 100% electric heating and cooling in this case. There's no actual need for that peak load heating system, but you can bring that in there as well. So it is, and you can, doesn't have to be natural gas backup. Again, it can be, you can have an electric backup, which the heat pumps basically do have built in if you buy a cold climate heat pump, or you can have other sorts of, even a wood stove if that's your backup for your system. So again, same thing here. The fraction of heat delivered, this is the same project, kind of the same instruction manual. We just wanted to kind of go over it again, illustrate you can drastically reduce the capacity of your systems using peak load heating, taking advantage of that kind of how that graph works that I showed you earlier, kind of a load duration curve somewhat, and get almost like in this case an 87.4% reduction, which most organizations that we've worked with, that's beyond a lot of their goals they have as of right now. So depending on the financial case, again, prices, work all that together. RETScreen allows you to kind of bring that in, play with different scenarios to kind of get the right situation for your organization. So that's how you do kind of the whole facility. Now, I think what Steven's going to do is going to do method 2B, where if we have a partial section of your building you want to electrify as opposed to the entire building, which is a common situation we run into. So you have a large facility, even something like a data center, if you want to isolate that from the rest of the building. So
Great, thanks, Adam. That was very good. Like, and there's going to be repetition here, and I think that this, even though it's a small area of RETScreen, there's enough complexity in it that the repetition, I think, hopefully will help you to see how to do this. I'm going to encourage you when you're finished today or within a short time afterwards, is to go out and have another crack at this. We got Greg Rusby online. Greg, you don't have to go and practice this because you know how to do this, I think, with your eyes closed. But so there are a few people that out there that use these methodologies, but hopefully more people do it. I'm surprised that the number of people that I run into who use RETScreen that really are not aware of the power heating cooling models, and we're not even using it for its fullest capacity because it's really designed to begin with a combined heat and power model. It can be used for heat, power, cooling model. It's got a lot of different iterations. In fact, you can do a district heating system within it as well. So it's actually very, very powerful tool. We're just using even a very small part of it today. So, in this example, I'm going to walk through, and eventually I'm going to open up RETScreen and just tweak it a little bit. We're going to start with an archetype, which is the 30 to 40% energy reduction archetype for a warehouse and storage facility. So just like that picture I had at the beginning, big warehouse with a small office at the front. And our goal is we want to electrify the heating and cooling or heating of that office area. But we don't know, we don't have a meter on it, so we're going to use RETScreen to estimate what that might be. So the initial facility, and this is the archetype as it exists in RETScreen, simply it has a heating system, which is a heater, right? An air conditioning system, which is basically some type of air conditioner. There's an office in a warehouse. So in this case, the building envelope, right, is heated and cooled, right? Whereas in the warehouse, there's no cooling, right? So that's the other complexity here. So we're going to work with the office, and then for ventilation, we're going to work with the office. Again, there's heating load for ventilation in the other areas of the building, but there's no cooling load. So they don't provide cooling to that warehouse area either. There are lots of internal heat gains in the facility. So the first thing we're going to do in this is we're going to add, or what I've done, and also, again, I'll send these files out afterwards. I'm going to add a rooftop unit, okay? And that rooftop unit in the base case is going to be exactly as the archetype was. I think it's a 75% efficient heating system. But then we're going to replace it with a heat pump in the proposed case. Now, we're not actually going to use the energy model to generate the savings, but I did do this for completeness. I'll show you what it looks like when we get into RETScreen. Same thing on the office. For the air condition, or sorry, for the cooling side of it, we're going to do the same thing. We're going to use that rooftop unit to provide heating in in the base case as it is today, just a simple natural gas fired unit, and we're going to convert that to a heat pump based system in the proposed case. Again, we're only going to be doing the office area, right? So here is our base case heating system, right? As I described, the natural gas system, and then the proposed case system. In this case, I'm using a 200% efficient air-to-air heat pump, 200% efficient, or a COP of 2 on an annual basis. And then the same thing on the cooling side of it. Here I've got a COP of 3.5 in the base case and 5.5 in the proposed case. Typically, your cooling systems on heat pump based systems are quite a bit more efficient. Central ones maybe less so than the mini splits. I'm actually quite amazed at how efficient a mini split is at cooling. So it's certainly not to be sneezed at. So what I'm going to do then is I'm going to go back to the RETScreen model. So this is still within the traditional energy model of RETScreen. And I'm going to determine, right, what I'm going to do is extract the net heating and cooling energy. So in those terminology I talked about before, remember, energy in the base case, that's the net energy, net of all the internal heat gains. So the lighting has already been netted out against this. So the total heating energy, net heating energy, is going to be the 12,000 here, kilowatt hours, plus that's for the envelope, plus the 98487 for the ventilation. So we got 21.5 for the heating energy, and likewise we're going to add the 9877 1845 for 11,722 for the cooling energy, the net cooling energy. Okay, so those are the two numbers we're going to use. Now we're going to go over and we're simply going to, as I showed you earlier, I'm simply going to change, right, the facility type to power heating cooling, and that within the same file now, right? So we've got the energy model, the traditional energy model is over there, still in there, nothing gets deleted. We're going to go over and we're going to go into the power heating cooling model, okay? We're going to enter, or we're going to select that we're doing heating, cooling, and not power. So we could use this as a cogen or a trigen system, but we're simply using it for heating, cooling from one source of fuel, which in this case, electricity in the proposed case. We've got natural gas. I have assumed values of 40 cents a cubic meter and 8 cents a kilowatt hour for the electricity. And we'll talk about that later on. This does make a huge difference what those, the relation is between those two, because obviously you got to trade one off against the other. But there's some interesting ways to do that potentially. All right, so next thing I'm going to do is I'm going to go into that heating load screen, and this is the one Adam showed you a little bit earlier, a couple times, and I'm going to tweak this watts per square meter till I get 21.6 total heating energy. So that's well, close enough, 21.5, 21.6. Okay, so what I'm doing is I'm calibrating my power heating cooling model to the net heating energy that was generated on the other side of the energy model in RETScreen. All right, that's the heating load. I can do the same thing for the cooling load, right? So I'm going to go in and I'm going to adjust this 49 to get the 11.7 or 11.7 megawatt hours or 11,700 kilowatt hours. Okay. Now it's interesting, in the older versions of RETScreen, you could do what's called a goal seek, where you could say, I want this number to be 11,722. Tell me what this number should be, because RETScreen was based in a spreadsheet back in the day, and it was pretty easy to do this. You got to do it manually in this one. So you got to be the goal seeker here. All right, so then ultimately RETScreen, as Adam has showed us before, will then determine the heating and cooling loads. So here we have the heating cooling energy, the 21.6 and the 11.7. And here we have the heating cooling loads, the 10.5 and the 7.4. And those are actually on these screens too. The 7.4 is right here, right? And the 10.5 is over here. I don't have any measures that's going to reduce that. I'm simply going to take it as it is and electrify it, basically. All right, just a quick reference to the engineer e-textbook that Adam put in there earlier. If you want to understand how this model works, it's quite a piece of work. It was originally developed by a good friend of mine, Urban Ziegler, who passed away a number of years ago, great employee at RETScreen, and it uses what's called the 13-month method. So basically, it takes monthly data and it allows you to do a sizing calculation, even though monthly typically can't do that. It's kind of an innovative approach. If you're interested, have a look at it. There's probably 20 pages where it's all laid out in excruciating detail. And if you are a technical person, it might give you a lot more confidence in how this model actually works. Now, again, as Adam said before, would I go straight to the contractor and order something at this size? No. I've actually done this a couple times. I actually had a part of a building that we're looking at putting a heat pump in, and I went through and I used RETScreen to do this. I had the contractor come in, who's a good friend of mine, and he went through his calculations, and we came out within 10% of one another. So I was actually quite impressed, right? He was actually quite impressed too, to tell you the truth. But so again, to be validated, to be verified, but it certainly gives you a good starting point. All right. So now what I'm going to do is I'm going to go enter in the proposed case cooling system. And what I'm going to do here is I'm going to push this to 100%. So I'm going to say the capacity of my cooling system can meet 100% of the load required. So this red screen pops that number out there. I call it the load coverage. So at that capacity, how much of the cooling load are we covering? 100%. All right. And I'm going to enter it in the COP of the proposed case cooling system being 5 in this case, and that's the same as we talked about before. So I'm now going to work down my list. I'm going to go to the heating equipment next. I'm going to select heat pump using electricity, and I'm going to basically put my capacity of my heat pump in, regardless of what I might actually be able to buy. Okay, at this point, I'm not worried about what I'm going to see what I need to cover 100% of the load. So I put 100% in at a seasonal efficiency of 200% or a seasonal COP of 2, right? And basically, and what I've missed in this one is the cost on the screen, but when we get into the software, the cost is actually in there. So I would have a cost in here, and what I did was I used the internal database to RETScreen to cost it, so I'll show you how we did that a little bit later on. But let's have a look at how much of this load and how much of this energy we can actually cover, and then what the carbon reduction is. So here we go. All right. Now, in this case, it's telling me if you click over this caution here, it tells me I don't need a peak load heating system, right? Because basically I've covered the load 100% and covered the energy 100%. Okay, so that's the starting point. No peak system required, but that's alerted to you, even though you have it in there implicitly. And then ultimately it will show me on the system summary screen what I'm going to be using in terms of consumption of fuel before and after. So we've basically eliminated the natural gas in the proposed case, right? Even though we have capacity to use it. All right. So the emission reductions are 99.7%. Now I've modeled this one in Quebec, but depending on where you are, I mean, it will be slightly different. But remember, I've taken all the natural gas to electricity, and the electricity in Quebec is at a relatively low factor. Ontario, we're a little bit higher than that, but still not a terrible number. All right. So this is the part where it gets a little disappointing because I'm looking at this. I put a 2% inflation rate on my energies, which is both natural gas and electricity, project life of 20 years, and I don't get a payback within those 20 years. Okay. And it's interesting. I see a lot of stuff today in the news about people. I put a heat pump in, my cost didn't go up, which is fair. But did your cost go down enough to pay back the investment in the heat pump? Maybe not. Okay. Now, having said that, I've done heat pumps where my goal is simply to reduce the carbon. It's not always about getting the financial benefit. So we can see that. We definitely have done the carbon reduction, and if that's what you want to do, that's the goal you have, the overriding goal, then you can hit that pretty easily. But we can work on this financial piece, right? So what I'm going to do is I'm going to go in now, and I'm going to open up this model in RETScreen. I'm watching our time here. We're doing pretty good here, Adam, on the time, so we can kind of elaborate a little bit if we have to. So I'm going to jump into RETScreen now. I'm going to jump into my, let's see here. This is the hybrid, but I'm actually, I've got the cooked, there we go. So this is the 100% one. So I'm just going to take it from the top. So again, this is systems in Quebec or Montreal. So I've selected the power heating cooling model, but I'll just go over and just show you. So under the commercial, I'm going to go back to commercial institutional. Okay. This is where I'm flipping back to the more well-known model in RETScreen. So here we see it. Okay. Here we see the system, right? Here we see the heat pump, right, itself, which is going to replace the rooftop unit, which is fired on natural gas. Now, in RETScreen, you can actually, in this model, you can actually put a percentage that's going to be supplied by the heat pump and a percentage that's going to be supplied by your backup or your peak load system, right? But The problem is you don't know where that percentage comes from. Now you could guess at 70%, and based on the graph Adam showed us a little bit earlier, that wouldn't be too far off the base, right? But what the nice thing is we can now go and use the other model to tell us what that percentage is probably more realistically at. All right, so I'm going back to my include screen. And so, and here's my heating and cooling load. So I've got my office, right? And obviously, how did I model the office? Well, there's all the details. So it's not just a number. It actually comes from the physical characteristic of the office. So we can use the physical envelope model in RETScreen to model that base case. Now, I do have a proposed case in here, which may or may not be different, but I'm not going to use the proposed case to get the final result. That's where I'm going to flip over to the energy or the power heating cooling model specifically. I think that's about all that I need to look at here. And again, the one thing to keep in mind, and maybe the one weakness of this method is the way RETScreen distributes the internal heat gains. So some of those internal heat gains may not be will come from the warehouse, but because of the way the RETScreen does the internal calculation, it doesn't identify where those are. So in some cases, what you'll want to do is to make sure to adjust for that you may not apply. I'm sorry, I'm going to go down to my lighting loads here. Just let me jump back there. RETScreen seems to have a delay when you're working in, there we go. I'm going to go to the warehouse lighting, right? So this warehouse lighting can contribute to the heating loads in other parts of the building. So what I will typically do is I will derate the impacts a little bit to account for that. So I'm not overcompensating. Sorry. Lights, office, there we go. Yeah, so here I'm using a 70% derating factor. I actually have 0 in the cooling in the warehouse because we don't actually cool the warehouse. And again, we could use, as Adam pointed out, I could go back here and I could actually use the percentages of fuel saved in heating and cooling, right, to then reduce the load in my power heating cooling model, right? But right now, what I'm going to do is I'm going to do it straight up, right? So I'm going to go back to my include screen. I'm going to sum up, right? These two numbers here, the 12,000 and the 9,000 give me 21, and the 9 and the 18 give me the 11 and change. So these are the two numbers that I'm going to use. So you kind of have to do a manual calculation, but it's not that difficult really. Again, going back to the slides, we tried to lay it out in pretty simple terms. Okay, so now I'm going to go back to facility, commercial, institutional, but now I'm going to slide up here. It's always a little hard to find. It's above, right? Power heating, cooling, nothing else changes, right? But now when we go over to the energy model, get there here in a second. There we go. We'll go to energy model. Everything looks different. So let's just kind of walk through this. I want to explore the different areas because I know we've done it in bits and pieces, but I want to take a bit more time. So the system selection, you can specify what the system looks like. You can tell it there's going to be power in here. When you click that, it's going to add other power characteristics. So this is more of a tri-gen type of system, right? We're not doing that today, but so we can turn that off, right? So we simply want to provide heating and cooling capacity from one source of fuel. In this case, to begin with, the heating is electricity, or natural gas, cooling is electricity, eventually all electricity. We enter our prices. So here I said before, 40 cents a cubic meter for the natural gas, 8 cents a kilowatt hour for electricity. We move to the heating load, right? Now, here I have in here my floor area. And again, this floor area has to match, right, the area of the building that you're dealing with. So this isn't the entire floor area of this building. This would be the floor area of the piece that you're actually working with. And then you would enter this 70. So I'm going to change this to 140 just for fun here. And you'll see that all these numbers below will change, right? Because what it's doing is it's calculating the heating energy and the heating load and the fuel consumption and eventually the cost of fuel based on this watts per square meter. But that's wrong. So we put it at 70. And to show you where Adam got that other estimator, if I click on the heating load for the building, it brings up a little help screen here, which I can maximize. And I have my building heating load chart. And this is the chart that Adam talked about before, right? So I could simply shortcut this whole process we're doing if I wanted to by knowing the floor area and estimating the heating load. So where would I get that from? Well, I would go back to my location page. And at this location, it tells me my heating design temperature is minus 21 degrees C. Okay, so now I'm going to go back to that help screen, if I can find that here somewhere. So 21 degrees C, and there's a highly scientific classification of insulation in the building: poor, medium, or good. So if I had a good insulation at 20 minus 21, we'd be looking at somewhere around 60 watts per square meter, right? So this building is looking at like it's coming up around 70 watts per square meter. So I could go back and I could look at the insulation in the building envelope. I suspect it's probably what I would call medium insulation. It's not poor. It's not like R5 in a wall. It's not good. It's not R25. It's probably somewhere around R12. Okay, but it kind of all fits together. So that's a useful chart. You can simply use that chart and work through this as well. But the method we're showing you is a bit more specific to the building that you're working in. All right, so I'm going back to my energy. So the key thing is to come up with that number there. Now, because I only took the ventilation, the heating energy for the part of the building I wanted, I don't have to worry about this hot water heating baseload demand. Adam, you excluded it before. In one case, you included it. You might have to put it in there depending on whether the numbers you enter in here. You know, if you only have the total cubic meters of the building, and that total cubic meters of natural gas provide ventilation, envelope, and hot water, you're going to have to put that estimate of what the hot water is in there so it can extract it when it calculates the heating and cooling load, right, for the weather-dependent functions. Again, we can enter in reductions if we want to do something before we electrify to reduce the load even further. We can do that in here, and we can add the cost of those measures in. That will always obviously be rolled into the financial case. Now, just looking ahead here a little bit, this model, we're only scratching the surface of this model, okay? So for those that are maybe more advanced, you might have seen some of this before, but others aren't. This is a single building or a single part of the building, okay? So we could have single, building with multiple zones. So I could actually build up multiple areas of this building and do the same thing in each zone. It's going to sum it all back up, or we can electrify it individually, or we can have multiple buildings. And what we're getting into here is a district heating system, okay? And then we can even add a space heating, space heating is weather dependent, but process heating is non-weather dependent. So that becomes more of a baseload type of heating requirement. So there's a lot we can do with this model. Again, I'm clicking all around, but I'm not destroying my model. I'm going to go back and click on what I had here, single building, turn off the space heating, and I'm back to where I was, okay? So don't be scared to explore these models in RETScreen. There's a lot you can do with them. And like I said, the power heating cooling model is a really interesting one. Whereas we don't see those little video help buttons up here, there is an extensive video on the RETScreen's YouTube e-learning channel, which goes into a lot of detail about how to use this model and all the different variations of it, including the district heating, if that's something that's interest to you. Okay, the cooling load. Let's take a look at the cooling load. Same thing, right? We're using electricity in our base case, 3.5, and we adjust the 49, right? And again, there's the same thing. We could go and get a graph and take a look at the cooling load if we want. So I'll just pop in there and just show you cooling load for the building. And you have another building cooling load chart, which looks very similar to the one we looked at before. So you need to know the heating or the cooling design temperature, which is probably around 25. So for medium, this would be about 37, 38. Where did it come in at? Well, 49. So that was a little bit off. So sometimes they actually line up pretty nicely. Sometimes they can be a little bit off. Let me just check the design temperature here and see whether I was off on that. The cooling design temperature is 30. Okay, so I was probably a little bit off on the cooling design temperature. So let me jump back in here, and I'm going to click on the cooling load for the building, cooling load chart at 30, medium. Yeah, so it's getting up there. So, and maybe this building doesn't have good windows, okay? How would, well, because the insulation takes into account the windows, right? And if these windows have a high solar heat gain, that's going to increase the the cooling load. So apparently, the cooling load in this particular building deviates a little bit from what that chart would predict for the heating, but it's likely because of the solar heat gain on those windows not taken into account. All right. Again, we can do improvement measures but ultimately it's going to tell us what the load is. So here we have our loads, right? 10.5 kilowatts, right? And again, I mentioned before, you can actually express that as other types of units. So BTU per hour, a million BTU per hour. I'd like to see it say tons there, but that's just my own preference, but it doesn't. 10.5 kilowatts on the heating side and 7.4 kilowatts on the cooling side. And it actually shows you what that looks like throughout the year as well. And again, if you had your base load hot water, it would actually appear here, but it would be excluded from the calculation when it comes to the actual space heating equipment. Okay. Let's move over to the cooling equipment. So I said I sized this. So I took the 7.4, right? And if a little trick in RETScreen, if you want to see what the real number is underneath with decimals, 7.35. Click on it. So in fact, when I put 7.4 over here, it says you're doing 101%. Okay, close enough, but it is an issue, right? So there we go. So we've got our COP of 5, and then this is the cooling energy delivered, the 11.7, again, like just to corroborate what we had before. Now we move over to the heating equipment. It's going to be a heat pump, and I'm going to size it for 100%, so 10.5. So in this case, the 10.5 is probably 10.5, right? So no decimals on that one. Decimals are important if you want to make these things match up, although in the big scheme of things, it's only a little bit. All right, so 10.5 kilowatts of heating capacity, a COP, a seasonal COP of 2. Now, cost. Where do we get the cost from? Okay, what I did here was I went to the cost database, and I kind of cheat a little bit because I grabbed the air source heat pump 760. So this is basically buying a heating system straight up, right? A heat pump. But I said, well, we're going to be replacing rooftop units. So I said, well, I'm going to use the 760. It could be even less than that if I was looking at the marginal cost, because I got to replace the unit anyway. I got to put the more expensive heat pump in. So I'm taking the marginal cost as being about $760 per kilowatt of heating. Give or take, right or wrong, that's what I'm going to do in this example. In your own situation, I would encourage you to think this one through yourself, what you use there. But nevertheless, then it tells me that the cost of the system would be $7,980, okay, for this heat pump system. And, let's just see what that does. Well, look at that. Okay, we don't have this payback, right? So I mean, that's always the end. You want to go see the financials, but the financials aren't always as important as the carbon. Well, and that's what we see here. We go back to our energy model, right? In fact, we can look at the system characteristics, and it's telling me, what is it telling me? You do not need a peak system, so I can get rid of the peak system, right? Drop that out of there. And now it tells me I'm meeting 100% of the capacity requirements, the load, and 100% of the energy requirements. 100% of heat is covered by the heat pump. But the problem is I'm into a situation now where if I have to show some kind of a return from this, right? And I think most of us today will realize that, electrifying isn't going to give us a 1-year simple payment or a 5-year. It's going to be a longer return. I typically like to use something like net present value or even a life cycle costing approach to compare these two, right? And RETScreen has those. I'm not going to get into the details of the level 2 model here, but RETScreen can give us a much more rigorous type of financial analysis, NPV, IRR, benefit to cost ratio. If anybody's interested, I even have a life cycle costing spreadsheet where you can compare two scenarios in parallel using the same calculations. But I think it's a much more mature way to actually evaluate electrification options. Do I do what we had before, or do I do the improved thing? I have to wait maybe 13 or 14 years for them to cross over. But over the life of that equipment, that low carbon electrified heating system will likely be the lowest cost in present value terms. All right, let's go back here. Let's play with this one a little bit, okay? Adam, what was that number you had on that little chart there in the e-textbook? I think it was around 70%, right?
Between 60 and 70.
60 and 70. Okay, so I'm going to go back here to my heating equipment, okay? And rather than taking 10.5 kilowatts, I'm going to put 7 kilowatts in here, okay? So I'm going to pick up 66.7, somewhere between 60 and 70%, right? I'm going to leave everything else the same, okay? Not touch anything. I'm going to go to my system characteristics, okay? So here we go. Now, what does it tell me? Now it tells me I need a peak system. So I'm going to click on the peak system. And I'm going to make sure that what's specified in here is right. Natural gas furnace, whatever the capacity is. I'm assuming that's about a 45,000 BTU furnace that's already in there. Okay, so that's probably what's there. But what's interesting here is that I'm only meeting 67% of the load, but because of the chart and the short duration of time you're actually at that high load, we're actually meeting almost 98% of the energy requirements, which means, right, from an emission point of view, right, a very high percentage of the emissions are being avoided, 97%. But that system is a lot cheaper now, right? And if we go to our finance, now we start to see something that has a more realistic return on investment if we were evaluating it from the point of view of return on investment. But maybe we could get an incentive, throw a $1,500 incentive in here, right? And it gets even better. And that doesn't even include any incentive that might come on the carbon side of things too, right? So, well, I guess one could consider that incentive I put in there as being on the carbon side of things, but there may be others, right? Let's see what the future brings. We can always be hopeful. So there we go. We've got a system that actually now has maybe a palatable financial case and a very attractive carbon case. Now I'm going to go back here. I'm going to remove this. I'm going to show you something else, okay? Um, in Ontario, and I know some of you may not be from Ontario, but in Ontario, um, if you're a large consumer of electricity, we call that a Class A consumer. Typically, if you're an industrial facility over 500 kilowatts, or if you're a commercial facility over 1,000 kilowatts, you actually purchase electricity slightly differently. And you purchase part of your energy based on your contribution to the five top peaks. Now, a heat pump may not contribute to the five top peaks in the province. Currently, we're a largely summer peaking province. So you might actually be able to effectively purchase the energy to run your heat pump, right, at 4 to 5 cents a kilowatt hour. Okay, I'm not going to give a specific number. I'm going to put in a number like 0.045. It really depends on the market here in Ontario. But for a Class A customer, if you can manage to not hit those five top peaks, you eliminate the global adjustment and based on this particular purchase of energy for the heat pump, so now you're working at essentially the hourly price of energy in the province on an annual basis. So I'm just going to put it in at 0.045. Now look at our heat pump finance, even without incentive. Throw another little incentive in there, $1,000, and this whole thing gets even better. So that's all I want to do today. I think that's pretty good on time. We're getting there. But the idea here is we want to be able to sort of come up, with this idea. I'm going to take part of the system, I'm going to electrify it. I don't necessarily need to meter it. I can do some simple modeling with RETScreen, determine the loads in that area, jump in, in a sense, preliminarily design a system, right? The heating load, the cooling load, what I'm going to replace it with, right? The heat pump of a specific size. Now, I still have to go out and say, okay, can I buy a heat pump that's going to have these characteristics? And we may find we have to buy more cooling capacity than heating capacity. But again, that's a detail beyond what we're going to cover today. But the idea here is it is possible to hybridize these systems. In fact, get to possibly what is a more palatable financial case. But in any event, you're going to have a fairly palatable and attractive carbon case. That's it for today. So, Adam, do you have any questions? Anybody else have any questions? We haven't had any questions here today. Did we answer all the questions? Well, I got a couple more slides. Encourage people to say things here. Just before we finish up, I'm just going to do a couple more things. So again, a couple slides just to sort of summarize what I just showed there at the end. So the slides, in a sense, the slide deck kind of gives you an instruction manual in a way. I encourage you to go through this, try it yourself. Not all HVAC systems are simple. Okay, not all of them are simple. And so we were talking today, what we had modeled in that archetype was what we call a constant volume single zone system. I'll just show you where that is. If I go back to my RETScreen model here, I go back to facility, um, and I'm going to go to change this to commercial institutional, okay? And then I go back in here under energy, if it sets itself, and I jump into the ventilation system, all right? So this is basically the model of a constant volume single zone system in RETScreen. That's the basic model. The other one you can do, method two, is kind of like a makeup air system. But those aren't by any means all the types of systems you have out there. You might have a variable air volume, constant volume with reheat. You could have a VAV with reheat. There's lots of different combinations. So, if you want to know how to use the modeling tools in RETScreen, which you might use for this purpose for subsystem modeling, there's a couple of really good videos. I'm not going to take credit. I was involved in them, but really, Michel Perrant is the genius behind those. How to use RETScreen to model more complex HVAC systems. So those are out there. There's videos and there's presentation decks that are available. Okay. So Jason says, can you discuss the difference in peak load heating and backup heating, a system as defined by the RETScreen? That's a good question, Jason. And that might be a question that I need to go back. Let me pull that up here if I can find that. So what you're talking about, Jason, is in here, you go into the system characteristics, right? Or even on the heating equipment, we can specify an intermediate load system, system characteristics. We can actually backup heating system. So let's have a look at what the backup heating system is, right? It, you indicate whether there's a heating system available. The backup system is designed to meet heating needs in the failure of the base load, intermediate load, and or the peak system. This is an optional requirement, and its use will depend on how critical heating loads are and whether or not the peak heating load is sufficient to provide all the backup systems. So essentially, the only way programmatically that this system would kick in is if I size this system so small that I couldn't. So let's say I made this system 2 kilowatts, and then it'll probably tell me that I need a backup. So what it says here, it's not big enough, right? So then I could actually add the backup heating system and just, right, to actually, and I put a capacity in this one of 3 kilowatts, and that will likely remove that. This is the system that's going to take up the load at this point. So I need to specify technology on that one. So Jason, that's essentially what it's all about. Is it's a backup to the peak load system, or one which would be used in an emergency when this system fails. It's really more put in there for completeness than anything else, but it will influence the cost if you require it to be in there. It's going to change the financial case. So I'll move this capacity back up to, do we have 7? Yeah, 7. Okay, so it's considered some other heating system instead of, yes. Yeah, it could be electric, could be anything. Yep. All right, look at our time. We're doing pretty good on time. That's good. I was worried that we wouldn't have enough time to do all this. Okay. Oh, thank you, Spencer. So hopefully, folks, this has kind of inspired you to maybe take a look at this approach. I'm just going to wrap things up pretty quickly with where did we go here? Oh, nice sunset from Prince Edward Island. There we go. As I was saying before, there are those videos. And just very quickly, what we've done here is we've looked at 3 ways to use the what I call the energy models in RETScreen, or the real property model with the power heating cooling model, back and forth moving data. Key thing to remember is you can have both of those active in the same file. Whichever one is displayed on the screen is the one that drives the results, obviously the carbon and the financial aspect. But they're both there, and you don't lose data when you move back and forth between them. The thing I just want to touch on before we finish off today is that we just touched one little thin slice of RETScreen. Some of the connectivity features of RETScreen that are now available are pretty phenomenal. If you use Portfolio Manager as a tool, RETScreen has automatic links to Portfolio Manager. It has many automatic links to other data sources. And it has, obviously, portfolio, so we can take a portfolio from Portfolio Manager, build our portfolio in RETScreen. We can, in fact, build out the statistical analysis automatically in the portfolio and create dashboard views. And one of my favorite ones, going way back 43 years, first time I ever did a demand profile for a building with a strip chart recorder and analog power meter is time series analytics. Really powerful. Um, even using gas data on an hourly basis to size up your heat pump systems. Powerful stuff. RETScreen has the tools to generate those low duration curves. So a lot of things that relate to what we did. But again, just so many different features in one package. We've just touched on part of them today. So why use RETScreen? Simplification, right? It brings everything together in one place. Standardization, so you're using, you can use the costing, you can use the factors that are built in terms of carbon and those sorts of things. I know some people will in fact request proposals from vendors and consultants in RETScreen or even results in RETScreen to standardize those results. Um, Persuasion, right? Some of the graphs can be pretty persuasive. We didn't look a lot of that today, but some of the graphics that are available can make some pretty persuasive and interesting reports. And as I just touched on there, and that other very busy diagram, interoperability of RETScreen with many other tools, sources, and so on. Now, RETScreen only will receive data from Portfolio Manager. At some point in the future, it may be able to push data back, but right now it's a one-way path in, but it can be automatically updated, which makes it really handy. And even though Portfolio Manager does a good job on benchmarking, RETScreen does a phenomenal job on detailed analytics beyond what you can do in those other sources, other tools. So if you haven't if you haven't got the free license, we'll send a video, we'll send the PowerPoint out afterwards, we'll send a couple of sample files we worked on for the warehouse and along with the license. And you know what I forgot here, Adam? Your name.
That's it.
Well, folks, that's it. It's